Now that we understand in detail how to do the training, we're just about ready to code. But before we start coding, let me ask you a question. Do you usually write all your code from scratch? I bet not. I bet most of the time you're like me and will try to find a library that can do some of the repetitive tasks for you. In R, there is such a library for handling machine learning training and evaluation tasks. The library is a package called Caret. Let's take a look at the Caret package and see how it can lessen our workload. The name Caret has nothing to do with vegetables or diamond rings. Rather, it's from the package's purpose, which is classification and regression training. The Caret package is a tool set that makes it much easier to perform training tasks such as splitting the data into training and test sets, preprocessing data, selecting which features of the data are most important, and tuning the model for better performance. In addition to these features, it provides a common interface for accessing algorithms. Now that we know about Caret, let's get into R and split the data and train the model. We have to load the Caret package before we can use it. To do this, we use the install.packages and library functions. Install.packages needs to only be run once. It will download the Caret package from the online repository and install it in our local installation of R. Once the package is installed, we can use the library function to load the package into the current R session. Remember that we need to use the library function to load the package whenever we start a new R session. Now we are ready to split the data into training and testing data. But before we do that, we need to set the seed we'll use for random number generation. If you're not familiar with setting the seed, let me explain. Inside the training algorithm will likely exist code that uses random numbers. Random number generators in computers generate random numbers in a sequence based on a starting point called a seed number. Code within R or the operating system will set the seed number for us if we don't set it. For example, if we generate integers between 1 and 10, the sequence might start with 1, 9, 5, and 8. If we do not set the seed, the next time we generate the numbers, they might be 2, 9, 4, and 7. This difference in sequence can change our training results. We want to ensure if there's a change in result between training runs, it's because of something we change, not because R or some other code decided to use a different set of random numbers. We can get the same random numbers by setting the seed. This will ensure that when we run our code multiple times, it generates random numbers in the same sequence. As we see, we use the set.seed function to set the seed value. The actual value we pass to the function does not matter, just that we pass the same value each run. With that understanding, let's set the seed for our training run. From our previous review of the data, we know that we only need a few of the columns in the data frame to train the algorithm. Specifically, we need arrival delay 15, the result, day of the week, carrier, destination, origin, and departure time block as features used to predict the result. We store these column names in a vector. This makes it easy to change columns if we decide we need to add or remove columns. Then we create a subset of the on-time data that contains only these columns. Notice that I again created a new data frame so I could easily get back to the data before the columns were filtered. Next, we need to split the data into training and testing data. If you think about this for a second, this can be kind of tricky. We need to ensure that we have the correct percentage of rows in the training and test data frames. In addition, we need to ensure that the distribution of true and false values is the same in both data frames. That is, for arrival delay 15, the ratio of true and false values is the same in the training and test data frame. We'll let Caret's createDataPartition function deal with this issue. We'll tell the function which feature it should ensure the percentage of its values are the same in the training and test data frames, namely arrival delay 15. Next, we'll tell the function what proportion of the data we want in the training set. 70% is 0.7, so that's what we'll pass. Finally, we'll tell the function not to create a list. We want one item per row. We run the function and it quickly creates a column vector containing a list of column indices. Let's look at these indices with the head function. If we look at the first 10 rows, we see createData has populated the column with the selected row indices. Notice how the row indices skip around certain rows. This is because the rows were selected to ensure that the proportion of arrival delay 15 with the value true is the same in this 70% of the data as it is in the original data. We use this row vector as the indices to select the rows that make up the training data by simply specifying the row indices as the list of rows to select. Pretty easy, huh? But wait, that took care of the 70% of data we want in the training set. R also makes it easy to select the 30% that are in the test set. We simply put the minus in front of the vector, and R will only select the rows whose indices are not in the vector. That is nice. So in 5 lines, we have partitioned our data into training and test data frames. But before we train with this data, we should verify that we really have a 70-30 split of data. We can do this by verifying the proportion of data in each data frame. First, we check the training data frame. It should be near 70%. That's very close to 70%. Then we can check the testing data frame, which should be near 30%. Very close to 30%. So on to training. To train the model, we use the train function. In the first parameter, we pass the names of the columns whose value we are trying to predict, arrival delay 15, and a list of columns used to predict that value. We separate the value and its predictors with the tilde character. Since we filtered the columns to only include those we needed to predict the value and the value itself, we can put a period after the tilde. This says all columns except the one on the left side of the tilde are used to predict the value. Next, we'll specify the data we use in training, which is our training data frame. Then we specify the method to use. The caret documentation contains a list of abbreviations. We are training using logistic regression, and this is a special case of generalized linear regression, so we pass GLM. To ensure we use the logistics regression algorithm, we also need to pass a secondary parameter called family set to binomial. We can now press the return key and R starts training. When the training completes, we'll have a trained model that we can use to predict arrival delays. And that's all we had to do to split our data and train the model. R and the caret package made this really easy. We just had to enter a few commands. You might be thinking we should take a look at the trained model and see how it works. So let's do that. Unfortunately, as you see, the data is not too usable, unless you happen to be the person that wrote the code for the algorithm or the model. The best we can do is get some statistics on the model. But don't worry, we'll see much better information when we evaluate the model in the next module. Let's briefly summarize what we did in this module. We started with an overview of the training process. This provided us with an understanding of the tasks we needed to do to split the data into training and test data and create a trained model. We then went into R and split the data and trained our model. To help us with some of these tasks, we used the caret package. This package contains functions that made it easy to split the data into training and test sets and then train the model. Join me in the next module where we will evaluate the performance of this newly trained model.